Leaving batteries behind allows to build tiny, cheap, and sustainable sensor nodes, enabling exciting new applications. Utilizing and managing the resulting vast infrastructure requires coordination and communication between the devices. What you see here is the capacitor voltage of a batteryless node over time. Most of the time, the device is inactive and charging its capacitor. Once it reaches the turn-on threshold, it can become active and turn on its radio to try and communicate with another node. These active periods are short and rare because of the low energy input and small energy storage capacity. As a result, the chance that two nodes are active at the same time becomes very small, making communication difficult. We examined a broad variety of lights and found that all of them exhibit varying levels of flicker at double the power line frequency. These brightness variations affect variations of the solar panel current on ambient light harvesting sensor nodes. We propose to exploit these current variations to provide nodes with a common, phase-synchronized clock. By aligning their wake-up times with that global clock, nodes can significantly increase the chance for successful rendezvous. We have designed an ultra-low power circuit to extract this clock signal and integrated it with a tiny batteryless sensor node powered by 3 small solar panels. The harvesting circuit regulates the voltage of the solar panels and charges a 47 microfarad capacitor. The FLYNC circuit filters the current signal and converts it to a digital clock signal. The wireless MCU uses this clock signal to schedule its activity. The demo setup consists of 2 such nodes connected to a mixed signal analyzer and powered by ambient room light. Let's first have a look at one node. The node remains inactive, charging its capacitor until it has enough energy and decides to become active. It switches on an LED until the voltage on the capacitor drops below the turn-off threshold. Let's record some data and see what's happening under the hood. The top graph shows the capacitor voltage over time. While inactive, the harvested energy is sufficient to charge the capacitor above the turn-on threshold. At some point, the node becomes active, switches on the LED, and quickly drains the capacitor before the cycle repeats. The second graph shows the bandpass filtered current signal from the solar panel. This bandpass filter is part of the FLYNC circuit on the node and amplifies the power line frequency component. The result is a pretty distinct 100 Hz sine wave that is phase locked with the local power line frequency. Next, we see the rectified clock signal that is generated by thresholding the sine wave with a comparator. This is the output of the FLYNC circuit that is connected to the MCU, which can adjust its local clock and schedule activity with respect to this signal. The last signal is connected to a GPIO pin of the MCU and is set high while the node is active. Let's now add the second node to the experiment. What you see now are the same 4 signals as for the single node, but this time for both nodes. So this is the capacitor voltage of node 1, and this is the capacitor voltage of node 2, and so on. Both nodes show the typical intermittent execution pattern, only becoming active at rising edges of the common 100 Hz clock. You can clearly see how both the current signals and the corresponding clock signals are in phase. This is not a great surprise in this setup where the nodes are right next to each other and powered by the same light source. Our more recent experiments indicate that the system also works across different lights, rooms, and even buildings. Zooming in more, we see that there still is significant jitter between the clock on 2 nodes as a result of component tolerances and noise. Because of their low duty cycles, the chance that the 2 nodes become active at the same clock edge is still not huge. But we don't need to look for too long as well. Here we see how both nodes had enough energy and decided to become active at the same clock edge. And, despite the small delay between them, they managed to have a significant overlap of around 200 microseconds, which would have well been enough to exchange a message. We are currently developing mechanisms to exploit the common clock signal for rapid rendezvous between batteryless nodes. So stay tuned and thanks for watching our demo.